It is customary to begin topology by defining open sets. We will be a bit different and define closed sets first. The reason for this is that it's easier to motivate why we need to study closed sets in the context of defining continuous functions. From the previous module, where we talked about the role of topology, the following definition should seem very reasonable. Let me remark that the definition I'm about to state is informal and intuitive, and you will see that this can be made precise once we have a precise definition of continuity using the tools of topology. So let me begin with an informal definition. Informal definition of continuity. So we take a function f from the open interval ab to the real numbers. We fix a point x in that interval. We want to talk about whether f is continuous at this point x. So what we do is we say f is continuous at x if for any set A subset of AB that is close in quotes, because we don't really know what close means, close to x, the set f of A is close to the point f of x. So why this is an informal definition is because we don't really know what the term in quotes close really means. All this is saying is, for a function to be continuous at a point, if you take a set that is close to that point, the image of that point and the image of that set should also be close to each other. So this neatly captures our intuition about continuous functions. Now let's try to make this notion of close precise. For that, let me first draw a graph of a function whose continuity we are trying to analyze. So let me draw the graph of a function. Let's say this is A, this is B. Let's say this is the function and this is the point x at which I want to see whether the function is continuous. Let's say what happens is, as soon as you touch x, the function sort of zooms, like the stock price of the software Zoom for the past few months. Let's say it just zooms. Now if you think about it, if I am taking a set that is close to the point x, surely you will accept that if I take, so x is actually here to be ultra precise, x is not somewhere in the air, x is here, this is the point f of x, this is the point f of x. Now if I were to take a set which is like this, sort of an open interval to the left of x, then if I choose a point here, if I choose a point here that is very close to x, and the value of that point is also very close to f of x. But if I choose a point, symmetric point on the other side, that's sort of going further away. Because this function is sort of just zooming, just one second, let me just not draw that curve in such a manner as to mislead you into thinking that it's not a function. Okay, so what we are really interested in is not just what happens to f of x, what happens to f of y when y is near x, But in actuality, what we are interested in is what happens to f of y when y is infinitesimally close to x. So we are not just interested in formalizing the notion of close. We are interested in formalizing what is the meaning of infinitesimally close. Okay, this just seems to have made our problem even more difficult. At least the notion of close has some tangible relation to reality, whereas this infinitesimal word seems even more complicated. If you recall, in high school, a ton of manipulations, algebraic manipulations in calculus was justified by saying this quantity is infinitesimally small and therefore can be neglected. Of course, due to the standards of the course that we are in, we have a high standard of rigor. We cannot do such things. So we have to make precise this notion of infinitesimally close. Okay. Now this is where this notion of closed sets come into the picture. So let's make the first definition in this chapter on topology. Definition. This is the definition of adherent point and limit point. The word adherent means sticks to the set. This is going to capture the meaning of a point being infinitesimally close to a set. And the limit point is a more refined notion of adherent point, which is very well studied and used in analysis. So the definition is as follows. Let A subset of R be a set. We say X in R is an adherent point. Again, adherent means sticks to the set. Is an adherent point of A if we can find a sequence xn. All of the elements of xn have to come from A such that xn converges to x. Furthermore, if the sequence xn comprises distinct points, that means there is no repetition in this sequence, then we say X is a limit point of A. So at the outset, it should be obvious that a limit point is automatically an adherent point. So this adherent point captures the idea that a point X is quote unquote infinitesimally close to the point to the set A. So what we are saying is the point X is adherent to A if you can find elements of A that converge to X. If you think about the definition of xn converging to X, what this is really saying is no matter how close to X I get, there is always a point in the set A that is closer to X, right? That's the only way by which there can be a sequence xn converging to X. Now, first lemma, which is so obvious that I'm going to leave it to you. Lemma: if X is an element of A, then X is adherent to A. Well, this is utterly obvious. If you have an element that is already in the set, it is infinitesimally close to that set. In fact, its distance from the set is in some sense 0, right? So this is such an obvious lemma that I'm not even going to bother proving it. Okay. Now, let me give some examples to illustrate that limit points and adherent points need not always be the same. So, examples. First, let's consider our favorite open intervals AB and closed interval AB. Okay. Now, set of adherent points in both scenarios is equal to the set of limit points and both are equal to the closed set AB. Okay. Now, from the previous lemma, it's clear that every point in the set open interval AB will be an adherent point of both open interval AB and closed interval AB. Showing that it's a limit point is also not that hard. You have to construct a sequence that converges. That's also utterly easy. Same for the endpoints. It's not at all difficult to construct sequences that converge to the endpoints also. So in this case, the set of adherent points and the set of limit points seem to be coinciding. Now let's take a drastic example. Let's take the set 1 by n such that n is in the natural numbers. Okay. Now let's plot this set. If this is 0 and this is 1, you have this point, you have this point, you have 1/3 which is somewhere here. Okay, and so on. You have points getting closer and closer to 0. Now observe that by the fact that every point of the set is automatically an adherent point, automatically makes 1 by n a subset of set of adherent points. Now it should be clear to you that if I take any one of these red points, the only sequence the only sequence in the set 1 by n that converges to this point is a sequence that is eventually all ones. The same is true for this point, which is half. The only sequence in the set 1 by n that converges to half is a sequence that is eventually just half, repetitions of half. So none of these points are limit points. Okay. So here it seems like the set of adherent points and limit points are not even going to have a common point. But wait a second. What about our element 0, which is what 1 by n is converging to? By the definition of both adherent and limit point, 0 is both an adherent as well as a limit point. So the set 1 by n is sort of getting infinitesimally close to the point 0, right? So here the set of limit points is just one element, the element 0, whereas the set of adherent points is 1 by n along with 0. Okay, so these two notions need not always coincide. As a drastic example, any finite set has no limit points. Okay, and the only adherent points are the set itself. The only adherent points are elements of the set. Excellent. So this is another drastic example. So we have somehow captured the fact that a set is getting really close to a point. Now I come to the central definition of topology. In fact, many will say this is the second central definition, but it's really the same definition of closed set. A set A subset of R is said to be closed if it contains all its adherent points. That means the set contains any point that gets infinitesimally close to that set. Okay? So examples of closed sets, we already see that any finite set is closed. So is a closed interval. Before I proceed further with the study of closed sets, let's define what is called the dual notion of closed sets, which is the notion of an open set. For that, I need to define what it means for a point to be an interior point. The notion of an adherent point captures that a particular element is infinitesimally close to the set A. The notion of an interior point captures the fact that the point is fully inside the set A. So to make this precise, I need to recall that if X is in R, then the open ball of radius R greater than 0 is the set B of XR defined to be Y in R such that mod X minus Y is less than R, right? Or in other words, this is just the open interval X minus R, X plus R. This is also known as the epsilon neighborhood of X. Okay, now we can define the notion of an interior point and open set. Let A be a set. A point X in A is said to be an interior point if BXR is a subset of A for some R greater than 0. So the best way to illustrate this is, of course, by a picture. You have a set A on the real line. Let's say there are these finitely many points and there is this open interval and there are some more finitely many points. Okay. If you choose a point inside here, then I can of course find an open interval around this point which is fully contained in the set. Whereas if I am here, I cannot do the same. So it is sort of capturing the fact that a point is fully inside the set. Not only is the point there in the set, but some neighborhood of the point is also there in the set. Then we say that it's an interior point. So the definition captures our intuition of what it means for a point to be fully inside a set quite nicely. Okay. Next definition of an open set. A set A subset of R is said to be open if each point of A is an interior point. Okay, let's give one example at least. Example: any open interval AB is an open set. Well, how do you show this? Well, it's rather easy. If X is in AB, then let R by definition be minimum of X minus A comma B minus X. Okay, then B XR is a subset of AB. So what this says pictorially is, if I choose the open interval AB, choose the point X here, I am looking at the minimum of these two distances. and setting it to be the radius R. Then all I'm saying is, when you do this R radius ball around the point X, that is fully contained in AB. That's the way R was chosen. Okay. Now, it should be immediately clear to you that this lemma is true. I won't even prove this lemma, it's that easy. Any union of open sets is open. It doesn't matter, it could be you take infinitely many open sets also and take its union, it will still be open. Why is this the case? Well, if you take a point X in this union, it has to be in one of the things which you are taking a union, and that set is open, and that means every point of that set is an interior point, and now you can finish this argument. Okay, so now I've defined the basic concepts of open and closed sets. Let's proceed with our development from the next module. This is a course on real analysis, and you have just watched the module on open and closed sets.